Hello, my name is Ian Peake. I'm from the STEM Centre for Digital Innovation at RMIT University, and for this talk in IEEE ICIT 2021, I will be talking about simulation components in Gazebo. This work is a collaboration with Jan Olaf Blech and Ronald Bejarano at the Factory of the Future at the University of Aalto, and Joseph Ladelfa, a PhD student at RMIT. Today I'm speaking about work in my prior role as Technical Manager supporting student projects in the Virtual Experiences Laboratory at RMIT. In this paper, we investigated the concept of simulation components in robot simulations using Robot Operating System and the Gazebo simulation platform. For the purposes of this paper, by a simulation component, we mean a reusable entity consisting of both physical and virtual aspects, such as a physical model as well as control code, and specifically for use with Gazebo. We are reporting on simulation case studies that are somehow related or even connected to real physical environments, especially physical labs with robots. We are particularly interested in aspects such as composability, simulation fidelity, and performance, which are visible to users and impact on the context of the simulation as it is used. We expect that these concerns are highly relevant in the practical development of digital twins in industry, as well as mixed reality applications more generally. For this study, we are basing our observations on student projects involving simulations in the Gazebo platform. The projects were developed in RMIT University's Virtual Experiences Laboratory, or VXLab, in Melbourne, Australia, and the University of Aalto's Factory of the Future in Espoo, Finland. For composition, Gazebo provides several constructs including models, actors, worlds, and launch files. Of these, the most relevant are models. A model is concerned with the physical modelling of an entity in Gazebo, including the rigid body model with properties such as mass, articulation, friction, collision, and appearance, as well as invoking plugins for modelling primitives such as sensors and actuators. For simulation fidelity, we are generally concerned with the degree of correspondence between the simulation and the real world. For performance, we are interested in latency and computational load. Since 2013, the VXLab at RMIT has provided automation, visualization, and virtualization facilities to support software engineering research in industrial automation, as well as digital innovation in teaching. In particular, VXLab hosts so-called capstone projects involving small teams of final year students from computer science, software engineering, and information technology in 12-week development projects. Project goals typically involve developing demonstrators with a combination of automation, visualization, and simulation, therefore often involving aspects of mixed reality. Here we show the results of an earlier capstone project involving VXLab's robot Rosie, where users duel with a robot. The robot Rosie is assembled from a Rethink Robotics Baxter robot mounted on a DataSpeed mobility base. This is a mixed reality experience where a user interacts with a virtual reality combat environment. An enemy robot swings a sword which can be blocked by the user's sword. Laser bolts fired from enemy robots on platforms can be blocked by the user's lightsaber. Rosie provides tactile feedback to the user in the form of the physical impact of toy swords hitting each other. In the paper, we reported on 6 project case studies with reference to our concerns of composition, fidelity, and performance. In this presentation, we focus on a few of these projects involving interesting observations on these concerns, especially in relation to mixed reality scenarios and the interrelationship between these concerns. We focus on Followbot and RoboCoStack, involving a common simulation platform, as well as the DroneFloat project. The Followbot project ran in 2019. Followbot was planned as a physical lab project developed in the VXLab at RMIT where a mobile robot, a Mir 100, uses computer vision to follow a specific human wearing a distinctive coloured vest, with the intention that the robot will act as a carrier for tools and so on. Because delivery of the Mir 100 was delayed, instead the project was developed using an alternative robot, VxLab's Rosie, as a physical stand-in addition to a simulation of the Mir 100. A live test of the Followbot prototype where Rosie follows the user is shown here. The Followbot uses a colour detection algorithm to detect the orange vest. It sends a command stream to the mobility base to rotate and move towards the vest. A safety component intercepts the command stream and uses data from its 360-degree LiDAR sensor to ensure that the robot does not collide with any detected obstacle, including a human. The command stream sent by the Followbot algorithm to Rosie's mobile base was duplicated to the simulated Mir 100. The Mir 100 simulation can be seen in the bottom left inset, running in real time in parallel with the physical test. So it was possible to use the simulation to evaluate how well the command stream works with the Mir 100, or at least the simulated Mir 100, and ultimately the goal would then be to test the software with the physical Mir 100. After the Followbot project, the VxLab model from the Followbot project was packaged along with Baxter and mobility-based models, which were adapted from models provided by the robot vendors, as a gazebo world with a set of launch files. Then these were packaged with ROS and Gazebo as a Docker image with the intention to use the image as a simulation platform in later projects. In early 2020, the Delivery Team project was initially proposed as a physical lab-based project. However, due to local COVID-19 restrictions, the project was replanned to use simulation. The simulation platform was extended to support the VxLab robots and other features such as navigation and computer vision in parallel with student use of the platform, with information about bugs fed back to VxLab staff. In the process, it was discovered that the physical robot Rosie could not detect the presence of the Mir 100 due to the relative heights of the Mir 100 and Rosie's LiDAR detector on the mobility base. This discovery can be regarded as demonstrating a significant benefit of using a detailed simulation, since the inability to detect the Mir 100 had not been previously discovered in the physical lab. The RoboCoStack project was planned as a simulation project where a pair of physically remote robots are used to provide physical stand-ins for humans at two remote locations, so that each human can make changes to the remote block stack as though there is a single shared virtual block stack. The final version of the project provides a demonstrator where one of the two robots scans its local block stack, sending a representation to the remote stack for duplication. So here's the scanning part, and here's the remote stack where duplication occurs. Given that this scenario involves two remote robots which are effectively connected only virtually, therefore it was possible to construct a simulation of the whole system by composing two separate gazebo simulations, the scanning simulation and the stacking simulation, connected by a ROS feature known as remote topics. Also, in the slave simulation, where blocks are stacked, physical interaction between blocks is difficult to achieve without a very fine simulation time step. While this doesn't appear to have any relevant impact on fidelity, it does increase the CPU cost and decrease the maximum world time of the simulation. Marker recognition is inaccurate in the simulation as for the real world, but it was not possible to make a more detailed evaluation regarding marker recognition fidelity. The Drone Float project was originally planned as a physical lab project. The context is the use of drones in postgraduate research by our co-author Josta Ladelfa, where users interact with drones in a way that encourages patterns of user movement. One application for such a system might be physical therapy. The plan for the research called for the use of virtual reality sensors held by the user to detect hand locations in real time, with interpretation of hand movements then causing drone movement and a feedback loop with the user. Due to COVID-19 restrictions locally, the project was replanned as a prototype using drones simulated in Gazebo and the PoseNet tool, which detects the pose of one or more people through an ordinary webcam. PostNet was developed as an example of a machine learning algorithm for computer vision by researchers at Google based on the TensorFlow platform. This project may be considered a mixed reality demonstrator in the sense that the human interacts with simulated drones rather than physical drones. The goal of the project was to evaluate the effectiveness of PostNet as an alternative to using the handheld virtual reality sensors. A further goal was to create a unified platform for VxLab simulation for scenarios where robots and drones interact, for example with drones carrying equipment to robots or landing on robots. Simulation latency is also an important aspect of fidelity, especially when the simulation may be used in real time to guide or respond to control of a physical system. For example, a simulation may be used as a safety monitor, causing an emergency stop in the physical system if some event occurs in the simulation. Here we show the experimental setup for measuring the delay between a simulation and the physical device. For testing purposes, the results of the simulation are displayed in a local machine alongside the physical robot. A script running on the same host as the web client monitors position or velocity data from the physical robot. Simultaneously, the same script captures the changes displayed on the 3D visualization rendered by the client, GZWeb. The fidelity test consists of executing a controlled iterative mission programmed in the robot. We compare the delay to a simulated Mir100 robot in the cloud with delay to a Mir100 robot in the local environment. The time difference or delay between the 3D visualization of this and the 3D visualization of the simulation and the local robot behavior is measured. We measured an average delay of 387 milliseconds with a local setup in Finland and a cloud provider in the Netherlands. In conclusion, we've evaluated examples of simulation components in Gazebo based on development case studies related to concerns of composition, fidelity, and performance. We identified Gazebo constructs which support aspects of composition for cyber-physical components. We identified noteworthy scenarios involving simulations related to real-world applications, including composition of multiple simulations and mixed reality. In particular, combinations such as physical robots generating test data for simulation and humans interacting with simulated robots. Possible future work includes more complex and distributed scenarios, including real-time control scenarios incorporating simulations, or use of an estimator to predict latency delays for simulation-based control. And finally, extending evaluations to simulation validity as opposed to fidelity, in which the emphasis is on fitness for purpose of a simulation. We would like to acknowledge the contribution of project deliverables, including video and screenshots shown in the presentation, by Aidan Schwartz, Roope Peikonen, Nicholas Huppert, Joseph Williams, Bryce George, Susanna Huang, and Thomas Funt. Thank you again to the organisers of ICIT 2021 and this track for the opportunity to present, and thank you for your attention.